So all year long I've been telling you about the importance of making sure all our answers are labeled in science class. It's very important to have units along with our numbers. If you look on your notes packet there, if I gave you lab instructions that said take 50 of the silver chloride and add it to 300 of water, stir and heat for 10, and then add 2.5 of the copper metal, that's a little confusing. Your brain might fill in those gaps with some previous experiences saying, oh, maybe grams, milliliters, minutes, seconds, whatever, but we don't know for sure. And so that's why it's important to have a system of measurement units, and that's what the IUPAC has set up. The International Union of Pure and Applied Chemists have set up this international system of units. We call them the SI units, because most other language, Système International. It's pretty much like the metric system. That's foundation, but then we have some other stuff added in, like the mole is an SI unit for chemistry. So let's look at this chart and look at the major things that we measure in chemistry. First up, distance, basically meaning dimensions. We can measure length, width, height, diameter, etc. In chemistry, we measure with a ruler. There's really no reason to use anything bigger than that, like a meter stick. The meter is the SI unit, and we can use variations of that, like the centimeter or the millimeter. And we love the metric system because it shows us the wonders of the power of 10. There's 10 millimeters in 1 centimeter. There's 100 centimeters in a meter. It's not like our system where we have 1 inch is going to be 2.54 centimeters, or there's 5,280 feet in a mile. So that's why we like our good friend the metric system. Next up we have temperature, which of course we're going to use a thermometer to measure. The SI unit is the Kelvin, and that's because we know as scientists that temperature measures kinetic energy. If there's nothing moving, there should be no temperature. And that's what this absolute zero reflects. When all particle motion has stopped, there is no kinetic energy, so that should be zero, and that's what we have. 0 Kelvin is absolute zero. Celsius isn't so bad. It is based on science and the power of 10. So like water freezes at 0 degrees Celsius, and it boils 100 degrees later at 100 degrees Celsius. So we have the wonderful magic of multiples of 10. A degree Celsius and a degree Kelvin is exactly the same size. There's 100 degrees difference between freezing and boiling for water on both scales. The only difference is we do have negative temperatures in Kelvin or in Celsius. So this is how we convert. If I have a Celsius temperature, I would add 273 to make it Kelvin. So like water freezes 0 Celsius, so that's 273 Kelvin. It boils at 100 Celsius, so that would be 373 Kelvin. And to go back, of course, you just subtract 273. So again, the degrees are the same size. The Celsius scale is just a little more user-friendly because it's based on water, the most common substance on the planet. Next up we have mass, which we're grateful to have our electronic balances to measure that with. We record all of the digits on the scale. We don't ever eliminate them. Even if the last digit is a 0, we write it down. And we know that's important now because of our sig figs. The kilogram is the SI unit, but our scales report the grams. We don't, again, you do any experiments in chemistry class that requires a kilogram worth of stuff. And of course there is a difference between mass and weight. Just a little reminder, like we talked about precision and accuracy earlier in this unit. Mass is constant, it's the amount of matter an object contains, whereas weight can change depending on gravity. Again, we interchange those words because most humans, we don't experience enough of a gravity change to really see our weight change. But again, on a technical level, just to know there is a difference between the mass and weight. Last up is volume. Volume is based on the meter, so the cubic meter is the SI unit for volume, although we use the cubic centimeter much more often. If an object is regular, meaning it has enough fiber in its diet. Ha ha ha. Kidding. If it's a regularly shaped object, we can measure its dimensions with a ruler and then calculate the volume. So length times width times height for a rectangular solid, pi r squared h for a cylinder, 4/3 pi r cubed for a sphere, etc. For a liquid, we'll just fill up a graduated cylinder and it'll tell us how many milliliters we have, which, again, a milliliter is the same as a cubic centimeter, or as we call it in the medical world, a cc, cubic centimeter. If an object has an irregular shape, we can measure its volume by water displacement, and this comes from Archimedes, who sat in the bathtub and noticed the water moving and figured out that it's exactly the volume that's put into it. And he exclaimed, "Eureka! He found it." And that's Archimedes' principle. So when we measure a volume by water displacement, the water moves by exactly the volume of the object that you put into it. And we'll see that in lab on Thursday. And of course, don't forget, when we do measure volumes, especially in a graduated cylinder, we want to watch the meniscus. We always want to measure from the bottom of the meniscus and not the top, because we can see that there's, kind of like an optical illusion, and we want to make sure that we always record the volume from the bottom of the meniscus. All right, until later.